In this video, we're going to have a look at the exponential function and the transformations that it can undergo. The standard form for the equation of an exponential function is y is equal to a times b to the power of x plus p plus q. And in grade 10, we focus on the influence of a, b, and q. To determine the form of the exponential function, we're once again going to focus on the mother graph, and we're going to have a look at two of them. Firstly, y is equal to 2 to the power of x, and y is equal to a half to the power of x. And to determine the form, we're once again going to determine a few coordinates and plot them. For this type of function, the ratio between the y and the x value is now exponential, and that means that the y value changes drastically. When substituting the first x value, you need to use your exponential laws to know that the y value is 1/8. Then we get to another part of exponents when we substitute 0, and there you need to know that anything to the power of 0 is 1. The bigger the positive x value that we substitute, the bigger the y value becomes. And here you can see that there are no negative y values, they simply become very, very small. When I now substitute the first x value into the second function, I once again need to know my exponential laws to say that this y value is 8. And again you will see that an x value of 0 gives a y value of 1, and that once again there are no negative values. The reason for this is that there's a restriction on the b value. The b value has to be bigger than 0 or positive. And when you take any positive value and raise it to an extra power, it will always stay positive. Let's have a look at why the b value should be positive. If we chose a negative b value, you will see that the y value interchanges between a positive and negative value the whole time. So we will start off with a negative y value of -2, then a positive 4 as it is squared, a negative 8, and then a positive 16. This does not form the same number pattern as all the other exponential functions. This b value can also never be equal to 1, because 1 to the power of anything stays 1, and then we'll simply have a straight line. In the first function, the y values increased as the x value increased. And for the second function, the y values decreased as the x value increased. You will also notice that the y values are exact mirror images of each other. When we now go and plot all the points for 2 to the power of x, you will see that they form an increasing curve. Similarly, if we plot all the points for a half to the power of x, you can see that this forms a decreasing curve. Both these functions intersect the y-axis at 1 because anything to the power of 0 is 1. You will also be able to recognize that both these graphs have a horizontal asymptote on the x-axis, or the line y is equal to 0. Even though both these graphs move closer and closer to the x-axis, neither of them will ever touch it and get a y value of 0, because this equation does not have a solution. Here you can see that the y value moves closer and closer to 0, but that it can never actually become 0. At the moment, we have a b value of 2, and earlier we saw that that forms an increasing curve. The bigger this b value becomes, the steeper the curve becomes. This b value can also be made smaller than 2, and then the steepness declines. Earlier I mentioned that the b value can never be 1 because then it will form a straight line. We also saw that if the b value is a half, we will have a decreasing curve. So you can see that when the b value is less than 1, the curve will be decreasing, and as this value moves closer and closer to 0, this decreasing curve becomes steeper and steeper. Therefore, we can say that a b value that is bigger than 1 forms an increasing curve, and a b-value that is smaller than 1 but also bigger than 0 forms a decreasing curve. Next, we can have a look at what the influence of the a-value is. At the moment, we have an a-value of 1. If I go and increase this a-value, the graph will be stretched vertically. This might look very similar to a bigger b-value, so let's quickly go and have a look again. When the b-value increases, you will see that the graph becomes more and more steep, but the y-intercept stays at 1. When I now, however, go and change the a-value, the y-intercept will also change because the graph is stretched upwards. And just like with all the other graphs, a negative a-value indicates that the graph is being reflected around the x-axis. So if I make the a-value -1, it will now become a decreasing graph below the x-axis. The q, or constant value, indicates exactly the same transformation as for all the other graphs. It shows how many units this graph is moved up or down. Here it is now important to also take into account the horizontal asymptote. If I make this q value bigger, the graph as well as the asymptote will move upwards. Here we can see that every coordinate moved up 2 units as well as the asymptote. This q value can of course also be negative, and that means that the graph as well as the asymptote will move down. And just like with the hyperbola, this q value does not indicate the y-intercept, but will show you where the asymptote lies. We can now say that a b-value bigger than 1 indicates that the graph will be increasing, and a b-value between 0 and 1 will be decreasing. The a-value indicates a vertical stretch, and the q-value once again shows an upward or downward translation. It also shows us the horizontal asymptote. In the next video, we're going to use this knowledge to sketch the exponential function.